So I've got three lines in R2, and I want to find their intersection. So the first one is 2x minus y is equal to 2. The second one is x plus 2y is equal to 1. And the third one is x plus y is equal to 4. So let's just graph these, just to have a visual representation of what we're trying to do. So I like writing my lines in y equals mx plus b form. So this top line becomes what? Minus y is equal to minus 2x plus 2. I just subtracted 2x from both sides. Or we could write that y is equal to 2x minus 2. That's that first line here. The second line, I'll do it in green. We could write this as 2y is equal to minus x plus 1. Or we could write that y is equal to minus 1/2 x plus 1/2. I just divided both sides by 2. And then this last line right here, we could write this as y is equal to minus x plus 4. I could go straight here. Y is equal to minus x plus 4. Now let me graph these. Let me draw an axis. That is my y-axis. I can call it my y-axis since we're actually dealing with x and y's now. And let's say that this is my, I'll do a slightly lighter, well, I'll do it in this gray as well. And say that is my x-axis, just like that. And this first guy is going to be 2x minus 2. So its y-intercept is going to be at minus 2. It's going to have a slope of 2, so it's going to be a pretty steep line, just like that. So that's that first line, just like that. 2x minus 2. The next line is 1/2 minus 1/2 plus 1/2. So if we go plus 1/2, that's right there. And then the slope is minus 1/2. So for every 2 we go over, we go down 1. So it's going to be like that. It's actually going to be orthogonal, right? Because it's the negative inverse of this guy. So it's going to look something like that. Let me draw it like that, just like that. And then this guy is minus x plus 4. So we go, this is 1, 2, 3, 4, and you go minus x. So for every 1 you go over, you go down 1. So this other line is going to look something like this. This other line, this last line, is going to look something like that, just like that. Now, I said at the beginning of this video that I want to find the intersection of these three lines. But notice, there is no intersection of these three lines. They all intersect the other two, but they don't all intersect each other in one point. We can kind of call the system as being overdetermined. We've overconstrained it. There is no intersection of all three of these points. So if I were to actually try to solve the system, I would find no solution. And to say that this has no solution is equivalent to saying that this matrix has no, or this equation has no solution. Let me write this. I'm just going to rewrite this system like this. This is equivalent to the matrix. Let me make sure I get this right. The matrix times the vector x, y is equal to 2, 1, and 4. And so this first equation is 2 times x minus 1 times y. So it's 2 and minus 1. 2 times x minus 1 times y is equal to 2. That's that first equation over there. The second equation, actually I could even, well, I won't color code it. That'll take forever. That's 1 times x plus 2 times y is equal to 1. And then we have x plus y is equal to 4. This system and this equation, this system right here, these are equivalent. Now, this isn't going to have any solution. You could try to find a solution to this. You could create an augmented matrix, put it in reduced row echelon form. But there is no intersection to these three things. So you're not going to find a solution to a times some vector, we could call this some vector x, is equal to b. Or another way to say it is that b is not in the column space of this matrix right here. Now, we learned in the last video that sure, we can't find a solution to ax equal to b. Ax equals b has no solution. No solution. We see it graphically here. These lines don't intersect with each other. And you could prove it for yourself algebraically by trying to find a solution here. You'll end up with a 0 equals 1. But we can almost get there by finding a least square solution. And we find a least square solution if we multiply both sides of this by A transpose. We know that A transpose times A times our least squares solution is going to be equal to A transpose times B. So at least we can find the closest fit for our solution. So let's find the vector x that is our least square solution. So what is A transpose times A? So A transpose looks like this. It'll have 2 minus 1, 1, 2, 1, 1. That is A transpose. And then, of course, A is just this thing, 2 minus 1, 1, 2, 1, 1. So A transpose A is going to be equal to, we have a 2 by 3 times a 3 by 2 matrix. So it's going to be a 2 by 2 matrix. So it's going to be a 2 by 2 matrix. So what do we get? We get 2 times 2, which is 4, plus 1 times 1, plus 1 times 1. So it's 4 plus 1 plus 1. So that's equal to 6. And then we have 2 times minus 1, which is minus 2, plus 1 times 2. So those cancel out. You get a minus 2 plus 2, that's 0, plus 1 times 1. So that's just going to be 1. And then we get minus 1 times 2, which is minus 2, plus 2 times 1, which is 2. So the minus 2 plus 2 is 0, plus 1 times 1. So we get a 1. And then finally, we get minus 1 times minus 1, which is positive 1, plus 2 times 2, which is 4. So we're now at 5, plus 1 times 1. So this is going to be 6. So this is A transpose A. Now, what is A transpose times B? A transpose is 2, 1, 1, minus 1, 2, 1. And then B is just the 3 by 1 vector, or the vector that's a member of R3, 2, 1, 4. So what is this going to be equal to? This is going to be equal to, let's see, we have a, this is, we get, this is going to, this is a 3, this is a, sorry, this is a 2 by 3 times a 3 by 1. We're going to get a 2 by 1 vector. We're going to get 2 by 1 vector here. So 2 times 2 is 4, plus 1 times 1, so that's plus 1, so that's 5, plus, let me actually write it down. I'm going to make a careless mistake. 2 times 2, which is 4, plus 1 times 1, which is 1, plus 1 times 4, which is 4. And then here you have minus 1 times 2, which is minus 2, 2 times 1, which is 2, plus 1 times 4, which is 4. So A transpose times B is equal to 9, and this is going to be 4. So we can rewrite this guy right here as the matrix A transpose A, which is just 6, 1, 1, 6, times my least squares solution. So this is actually going to be in the column space of A, is equal to A transpose times B, which is just the vector 9, 4. And this will be a little bit more straightforward to find a solution for. In fact, there will be a solution. We've proved it in the last video. So to find a solution, let's create our little augmented matrix. 6, 1, augmented with a 9. You put the 4 there, and you get a 1 and a 6, just like that. Let's put the left-hand side in reduced row echelon form. Actually, first I'm going to swap. I am going to swap these two rows. That's my first row operation that I choose to do, just because I like to have that 1 there. It's a nice pivot entry. So then I get, it goes to 1, 6, 4, and 6, 1, 9. And then let me replace my second row with the second row minus 6 times the first row. So I'm going to keep my first row the same. So I have 1, 6, and 4. And then my second row, I'm going to replace my second row with the second row minus 6 times the first row. So 6 minus 6 is 0. 1 minus 6 times 6. That's 1 minus 36, so that's minus 35. And then 9 minus 6 times 4 is 9 minus 24. This one always gets me in trouble. So 9 minus 24, that's the negative of 24 minus 9. So that is minus 15. Minus 15. Let me make sure I didn't make a careless mistake. 1 minus 36 is minus 35. 9 minus 24. 9 minus 24 is minus 15. So that's what I get right there. And then let me go to the right now. So let me divide this row right here, let me divide it by minus 35. So I'm going to keep my first row the same, 1, 6, and 4. And then this guy right here, I'm going to divide by minus 35. So I'm going to get 0, 1, and then minus 15 over minus 35. That's 15 over 35. Or that's 3 over 7. So that is equal to 3/7. And then if I really want to, well, let me just put this in complete reduced row echelon form. That'll be nice. Let me keep my second row the same. So my second row is 0, 1, and 3/7. And then my first row, I'm going to replace it with my first row minus 6 times my second row. So 1 minus 6 times 0 is 1. 6 minus 6 times 1 is 0. And then we have 4 minus 6 times 3/7. So 4 is 28/7. Let me write it up here. So we have 4, which is 28/7, minus 6 times 3/7. So minus 18/7, right? That's 6 times 3/7. So this is going to be equal to 10/7. It's going to be equal to 10/7. 10/7. And just like that, I've solved this new equation. So you could say that, let me write it this way. We could write that x star, this is going to, the first entry of x star, which we could call x, is going to be 10/7. Let me write this. X star, the solution is going to be 10/7 and 3/7. So I'm saying that if you take x is equal to 10/7 and y is equal to 3/7, you're going to get as close to a solution as possible. So let's see what that looks like visually. What is 10/7? So let me write this down. X star is equal to 10/7 and 3/7. Or we're saying the closest, our least square solution is x is equal to 10/7. So x is a little over 1. X is a little over 1. And then y is going to be 3/7, a little less than 1/2. So our least square solution is going to be this one right there. And so this, when you put this value for x, when you put x is equal to 10/7 and y is equal to 3/7, you are going to minimize the collective squares of the distances between all of these guys. And I drew this a little bit too small to show that. But let's actually figure out what our minimized difference is. What our minimized distance is. So remember, the whole point of this is to minimize the distance between ax star, is to minimize the distance between ax star and b, or between b and ax star. Now, what was ax star equal to? Ax star was equal to 9/4. So this right here, sorry, ax star, that's not equal to 9/4. That's A transpose ax star is equal to 9/4. Ax star is our original matrix A, which is this one right here. So 2, let me write it down here. I know it's off the page right now. So our original matrix A was 2, minus 1, 1, 2, 1, 1. That was our original matrix A right there. And then our x star, we were able to determine, is 10/7 and 3/7. So ax star is going to be this product. So what is it equal to? It is equal to, it's going to be a 3/1 matrix. So we get 2 times 10/7, which is 20/7, minus 1 times 3/7, so minus 3/7. And then we get, let me see, yep, that's 20, right, minus 3/7. And we have 10/7, and we have 10/7, minus 2 times 3/7, so minus 6/7. Or plus, sorry, this is a plus, right? 2 times 10/7 is 27, minus 1 times 3/7. Then we have 1 times 10/7 plus 2 times 3/7. And then we have 10/7 plus 3/7. 10/7 plus 3/7. So ax, so this is a, and x star, our least squares approximation for x, is equal to, what is this? This is 17/7, this is 16/7, and this is 13/7. sevenths. And we want to find out what this minimum distance is. So let's see. So this is going to be this thing. So 17 sevenths, 16 sevenths, and 13 sevenths minus our original b. Now our original b was 2, 1, and 4. So I'm claiming that my solution that we've just found, this minimizes this distance because this is the projection of b onto the column space of A. We saw that before. So our b we see all the way up here is 2, 1, 4, 2, 1, 4, just like that. So if we take the length of this, let me switch colors. This is equal to the length. Let me write all of this in sevenths. I'll just do it in my head. I don't want to waste too much time. So this is 17 sevenths minus 14 sevenths, right? 2 is 14 sevenths, so this is going to be 3 sevenths. And we have 16 sevenths minus 7 sevenths, so that's 9 sevenths. And then we have 13 sevenths minus 28 sevenths, so that is minus 15 over 7. So this is the vector that separates the b that was not in my column space of A from the projection of B. And if we find its length is going to be equal to, well, it's going to be equal to, let's find the square of its length first. The square of its length is going to be 3 sevenths squared, so that is 9 49ths, plus 9 sevenths squared, which is 81 49ths, plus minus 15 sevenths squared. So that's, what's 15 squared? 15 squared is 225, I think. Let me make sure. I'm prone to careless mistakes. 5 times 5 is 25. 1 times 5, this is 75. And then I have a 150. Yep, 225. 225. So plus 225 over 49, which is equal to, so 9 plus 81 is 90. And then, so 225 plus 90, we get a 5. Was it 315, right? So this is equal to 315 over 49. Or if we actually wanted the difference, right, that's going to be the square root of this. That's going to be equal to, so if we take just the regular distance, that's equal to the square root of that. So it's equal to the square root of 315 over 7. Over 7. And square root of 315, it looks like that is simplifiable. Does 9 go into it? Looks like 9 goes into it maybe 35 times. So it would be, what, 3 square roots of 35 over 7. So that is just a measure. This, you're not going to find, and let me put it this way, you're not going to be able to find any member of R2, any values of x and y, that's going to give you a smaller value than this when you find the distance between its solution and the solution you were trying to get to. So this, based on our least square solution, is the best estimate you're going to get. X is equal to 10 sevenths, y is equal to 3 sevenths. A little bit right, just like that. Anyway, hopefully you found that useful and you're starting to appreciate that the least square solution is pretty useful.